topic है length contraction, and length contraction is something which we again observe when something is moving at a speed comparable to the speed of light. Okay, so that is important. So the topic is length contraction. So we're going to understand this, and it's the logic remains the same. We do have an observation of a length from a moving frame of reference, okay, and from a stationary frame of reference. So let's just consider this is your stationary frame of reference, right? Let me just draw a longer line here. And then we do have a moving frame of reference, which is again moving with a velocity v. Okay, this is also there. So this is your moving frame of reference. Okay, this coincides on the other axis. There is motion only along the x-axis, right? So we can say that this is, let's say, moving with a velocity v. And what we are observing is, or what we are actually measuring is a length. Okay, so this is moving with a velocity v, and we want to measure the length. Okay, so this is our, let's say, S frame, and this, or maybe I can use the color code so that you are not confused, right? So it's in white, so let me just write this down as S frame, and this is in blue, so I'll just keep it in blue, and this is a S prime frame, right? And this is moving with a velocity v. Now I want to measure, you know, the distance between 2 points, let's say A and B. So I'm measuring the distance between the 2 points. So as soon as you hear the word length, we do have this concept that, okay, maybe we are talking about the measurement of a length of a scale, or maybe the length of a cylinder, okay, or length of a box or something like that, okay. But that's not the case. It might be that we are basically having two pillars, okay. We are basically having, let's say, two pillars, okay. These are the two pillars, and I'm measuring the distance between them. So that can also be coming under the effect of length contraction, right? So if you're moving very fast, and if there are two pillars, and if you're going to find out the distance, it will be different, okay, if you are standing there and measuring the length, okay. So if you're moving and measuring, it will be different. If you're standing and measuring, it will be different, and that's the idea behind length contraction. So it's a very simple idea here, okay. So what we are going to do is we are going to measure the distance between these two, okay, and we, you know, we can take out the x-axis, the y-axis, y coordinates and all, okay, and we can measure the length. So if I'm just observing it from this particular point, and I want to know what is the position of x, maybe I can write it down as x1, y1, z1, and the position of b would be x2, y2, z2. They are not coinciding, they are not on top of each other, so that means, you know, the coordinates will definitely be different, okay. So this things has to be clear. So I think it's very simple. So we are going to consider two events, okay. So let me just take events, okay, and let's mark this as E1, okay. You can use any notation, okay, there's no issues, okay. In event 1, so even if you're doing a measurement, that can also come under the category of an event, okay. So this is like measure the left end. So we are measuring at here, this is the left, this is the right, right. Measure the left end xa, so the coordinate is xa at t. So just to make it clear, xa like easily signifies that this is the x coordinate of a, so I've just written to the base a, right. This is one event, and the second event would be measure the right end xb at t. At the same time, we are measuring both the lengths. Now you might don't get confused between with the words left end and right end. If you, even if you omit this, this is fine. If this is not a point, maybe this is a slightly, you know, it's a broader point, you always measure at this particular side, and here also you'll measure here, and then that will give you the total length. And that's why I've written left end and right end. Even if you don't write down left end and right end, it's totally fine, no problem, okay. So now if you want to know what is the rest, okay, length, maybe you are in the s prime frame, okay, and you are measuring, it's moving with velocity v, maybe a and b are also moving, and you are measuring the length. So that means whatever length you are measuring would be the rest length, right? Because if a and b are moving, your frame is also moving, everything is moving together, okay. Let's say you are inside the bus and you are doing the measurement between a and b, okay, the length is not going to change for you because both of you, the person as well as the distance that you are measuring, are in the same frame of reference, okay. So in general what we can say is that this x coordinate, maybe I can take xb prime minus xa prime, okay, these are nothing but the rest length, okay. So this is rest length. So what we are doing is we are measuring the rest length, that means there is no change in the length, okay. And rest length, maybe you can just take it from here, and if you measure it from here to here, this would be xa prime, maybe this distance. And if you take this would be your xb prime, this distance. Subtract this from this or subtract this from this, you are going to get the length here, right? So this is the idea. Now what we can do is we can actually do it for event E1. Now E1, what was the case? It is at rest and this entire frame is moving along with A and B. This entire frame is moving towards this direction. That means you want to measure the length now between A and B from the rest frame, but then the frame is moving along with A and B, okay. So that is very important to understand here. So that's the idea. So what we can do is we can just simply write it down as for E1, okay. For the first event we actually want to know what is xa prime, let's say, okay. Xa prime we already know it's a part of the rest length, but if we want to write it down in terms of xa, what we can do is we can simply write it down as xa minus vt, okay, and divided by root over 1 minus v square divided by c square, right? So we can write it in this way. So that's the case. And if we just want to do it for e2, okay, for e2 this would be nothing but xb prime is equal to xb minus vt divided by root over of 1 minus v square divided by c square, right? So you've connected between xa and xa prime, xb and xb prime. You can take the relation from the transformation equation, right? Lorentz transformation we are taking. And here v is the velocity with which this frame is moving, or we can say with which the point A is moving, or we can also say with which the point B is moving, because all of them are moving with the same speed, okay. So this is the expression here. Now what I want to do is I want to find out this in the S frame, okay. So I can also find it out in x prime frame also, right? So I can just take xa prime minus xb prime, I can take this difference here, okay, and we know that is actually equal to the rest length, right? This is all mathematical, so I think there is no such confusions here. So I want to measure length of AB, okay, in S prime frame. We already know that if we measure in S prime frame, it is the rest length, okay, and that is actually given by xb prime minus xa prime. We already know it. But as per the relation between the moving frame and the not moving frame, that means the prime frame and the unprimed frame, we have these relations, so we can actually do that subtraction. So if you do it, this is xa minus xb, this is minus vt minus minus plus vt, so this vt and that vt will just get cancelled out, right? So if you take it xb minus xa, so on top you will basically get xb minus xa, okay, and then I can just divide it, okay, and I will get whatever is there in the denominator. So this is 1 minus v square divided by c square, okay. So you see that there is a change, okay, when we measure it from two different frames of reference, okay. So this is basically a mathematical expression, so there should not be any kind of confusion here as such. But if I just try to write down in a simplified way, I know xp prime minus xa prime is nothing but equal to the rest length, okay, the rest length when it is not moving, right? And this is the length when it is actually moving, right? So this is actually the expression for length contraction, which is very simple if you got this idea here. And this is actually something which you can again imagine. So you can consider this to be another example of thought experiment, right? So this is rest length. So if just like I wrote about improper time and proper time, here also we can do the same thing. The rest length, okay, which is nothing but xp prime by xa prime, okay, is equal to, now when you measure it from here, this frame is moving, okay, and that's the reason that it is written as moving length, okay. So whenever you are confused, you can think about the terms moving length and rest length, and it will be a bit more clear. So we can just write it down as the moving length because ये तो move कर रहा है, right? So what I can do is I can take this as divided by root over 1 minus v square divided by c square, right? So this particular relation is actually called the relation of length contraction, okay? So if you are observing it from a moving frame of reference, you will see that the length gets contracted, right? So in general, I can write it down as L naught is equal to, maybe I'll represent it as L divided by root over of 1 minus v square by c square, right? So that means if you want to measure the length on the moving frame of reference, you will observe it to be L is equal to L naught root over 1 minus v square divided by c square, correct? So this relation that we have is actually called length contraction. So there can be different kinds of problems, numerical problems. So I will test you with numerical questions maybe in the quiz or in exam, but I'm not going to give you complicated question, rest assured, okay? The questions will be quite straightforward, okay? But you have to understand the concept here and use the formula. Now the a simple, explanation for this is how to understand if this is length contraction, yes or no, right? When you multiply two quantities, it will be larger, right? But here if you multiply it, right, if you take, let's say, root over of 1 minus v square divided by c square, right, and let's say this v is this v is basically comparable to c, right? So it will be some value, but then c will always be a larger value, right? So that means this root over of 1 minus v square by c square, okay, this will be actually in equivalent to something like 1 minus whatever value is here, okay, whatever value you get, and this result will always be equal to root over a value which is less than 1, right? So finally whatever result you are going to get is going to be less than 1. So if you multiply a length, let's say 10 centimeter, with a value which is actually less than 1, okay, this entire answer will always be less than L naught, right? So let's take an example or a very clear picture here. That means if I write down something like 10 centimeter maybe and multiply it with a value which is less than 1, even if you take 0.9, right, the final answer that you get is 9 into 10, so that's 90 and point, so it's 9 centimeter, right? So it is 9 centimeter. Now 9 centimeter is less than 10 centimeter, which is actually nothing but giving you the expression for L. So you see, whatever length you considered in the moving frame when you are inside the frame, and if you are measuring that same length from outside, you are getting the length to be lesser, and that is the reason it is called contraction, length contraction. This can only be possible if this v is very high. Now if the v is very low, this entire value is going to be very close to 0, right? So analysis here is, if v is much less than c, this root over 1 minus v square by c square is equal to root over of 1 minus 0. This is just root 1, which is 1. So therefore the length that we measure in our daily life, whether we are in the moving frame or in the rest frame, the length appears to be very close to each other. So yesterday the problem that we have done, okay, this was actually a very good example of length contraction, and I hope you have already solved it. If you check, this is the result we have. So this plus, so this is very low, so we are considering it to be almost negligible, okay, that's why L is equal to L naught. But this is something which is after neglecting a lot of things. Okay, if we don't neglect, then we have to measure and check what is the relation for length contraction. So that was time dilation, and this is length contraction. Okay. So keep a note. There are so many questions which comes, different kinds of exams. Your general basic exam also, you'll have a question from these relations of relativity. Okay, very important. I will take one more topic now, which is actually again very interesting. This is actually called relativity of simultaneity. So I think I already told you what is simultaneity, but anyway, I'll just explain it. Relativity of simultaneity. So what does it mean? So in simple words, simultaneous means if two events occurs at the same time. अगर एक ही समय पे दो इवेंट हो तो उसको हम simultaneous बोलते हैं. But then this idea of simultaneity is again a relative term. It depends from which frame of reference you are observing the event. Okay, so if I am on a different frame of reference and the event is happening in, let's say, a moving train and you are outside the train, those events won't be simultaneous for you. But then again, the point here is that the motion should be comparable to that speed of light. So whatever idea we're going to develop now is again a thought experiment where we are going to discuss about simultaneity. And this is something which we imagine, when you were younger. Okay, these kind of logics, you had that logic. Okay, so don't worry, it is not something which you cannot imagine. So that's why these thought experiments really work. It does work. Okay, it's not a complicated topic at all. So let's say I basically have, let's say, a box or something which is moving. Okay, so I will just take a larger box here. So I have something like this. Okay, and this is not moving, so I basically have a non-moving frame of reference. Okay, and then there is maybe a bulb, a torch maybe, which gets switched on. Okay, and then there is a two doors here. There is one door D1 here, imagine the scenario, and then there is one more door D2 here. And as soon as the, let's say, I switch on the light, a pulse will set in this direction and also in this direction, right? It will go in other direction also, but I'm only interested in these two directions. As soon as I switch it on, okay, it's a bulb, centralized bulb. Switching it on, pulses will go. As soon as it hits the door D1, let's say, the door will open. It hits D2, the door opens. So the situation is, if it hits the door open, I have to analyze when does the door open. So I switch it on, it hits D1, it hits D2, the door opens. So in general, if you are inside this frame of reference, okay, you will see that both the doors will open at the same time. That is called simultaneous event, right? So the idea is very simple. Okay, so maybe I can write down here pulse. You can write down light also, no problem. Yeah, so pulse hits D1. If you get the idea, you can explain it in your own words. Whatever I write, it's just a guide. You can do it in your own words. It's not difficult. Door D1 opens. Okay, and then pulse hits D2. Door D2 opens. Okay, so this is maybe S frame. Okay, you're inside it. Okay, whatever you want to consider, you can consider S prime frame also. The only thing is you should be in that frame of reference. That is important. Okay, in S frame. So this is what happens. Now let's imagine we have got one more frame, maybe the S prime frame. Okay, so in that, what happens is you are observing the motion. You are outside. Okay, maybe you're in the S prime frame and the box is moving with a velocity v. Okay, so what we're going to do is we are going to draw this again. Okay, we're going to draw this again, maybe. Okay, it's the same color. So this is again the same thing happening. But this time you are not inside, you are outside. Okay, you are observing it from outside. This is D2, this is D1. Okay, and let's say this door is, moving with a velocity v. Let's say this not door, the entire region, maybe it's a train or a bogie which has got two doors connected to the two end. This is moving with a velocity v1 for you now, and you are somewhere here observing the event, right? The bulb switches on. Okay, pulse is traveling in this direction, and the pulse is also traveling in this direction. Now, by the time, okay, imagine this, it's moving very fast, the velocity is also very high. By the time, the pulse reaches D2, D2 has already moved forward. So that's why I need to draw one more image. So I will do it. By the time the pulse has reached D2, has already moved forward. Okay, and the new position, maybe you can overdraw this clearly. Yeah, and the new position would be D2 will be here. This is a new position, and what you observe is that the pulse has to travel a shorter distance to hit D2, but it has to travel a longer distance now. For shorter means, it will just travel this much distance. For D2, it's not the same now. It's going to travel this much distance for D1. So that means it's going to hit D2 before it hits D1. So what will happen? D2 will open first, D1 will open second. So what is happening here? That whenever you are in a moving frame, inside the frame, it's a simultaneous event. But when you are outside, it is not simultaneous anymore. It's going to happen at different point of time. Okay, and that is the idea of relativity of simultaneity. Okay, so this is very interesting. Okay, I hope this happens. Get a clear picture of this. Okay, let me just write it down a bit here. Okay, a few sentences will do, but I hope you get this. If you get this, I think you can write it in your own words. So S1 frame, okay, D2 opens. It also depends on the direction, obviously. I think this is quite obvious. Opens before D1. In which side the boxes or the train is moving. If the v1 is not in this direction, it is in the opposite direction, it will be the other way around, right? Then d1 will be closer to the pulse, so d1 will open before d2, right? Here d2 opens before d1. Okay, so this is what we observe. Okay, so this is important. Maybe what sentence, I didn't frame any sentence. Okay, from in when observed, maybe I can write down this, just help you out on the framing the sentences. Okay, when observed from outside, the pulse, okay, reaches D1 or D2 earlier than D1, earlier than D1, as the, what I can write on, box moves with velocity v1 towards the left. Okay, towards left. Right? I think this is okay to explain, but if you understand it, I think that's very simple, right? Hence D2 will open before D1. Okay, so this is very important. The same thing may happen if it moves in the other direction. So you want to add some more explanation to it, you can actually consider the box, and then you can say that this is moving in the other direction. So if this is the direction, this is again, let's say v2. In that case, okay, in that particular case, this d1, this is just a note, maybe d1 will open before d2. That's the idea. Okay, So, what's the concluding remark here, which is very important from whatever we have seen for a moving frame and a non-moving frame, right? What I want to conclude here is that hence two events are simultaneous is also a relative term. Is also a relative term. So this is also a relative term. It depends from which frame of reference you're observing, and then only you can say whether it is relative or not. How do we understand it mathematically? So we are going to do a very short derivation, and I think it's not very complicated. Okay, let's imagine this. Okay, let's imagine a scenario. We have the point here, and the coordinate is x1 t. We have another point here, and the coordinate is x2 t. Okay, we have an event e1. I'm just considering a general event, and I have the relation as t1 prime is equal to t minus x1 v divided by c square. This can be any event, maybe the door opening. So this is the position of that door x1, and this is the position of the door on the other side opening. So this may be x2. So if I want to connect t1 prime with t, I am writing this relation. On this side we have whatever we have in the s frame, so I'm writing it down as x1. Okay, divided by root over 1 minus v square by c square. Why I'm not writing t1? Because both the doors will open at the same time. So that's why this is T, this is also T, and not T1 and T2. That's the beauty. Okay. So what we can do is we can connect it with whatever we have in the prime system. In E2, we know this T2 prime. If it is moving at a very fast speed, obviously T1 prime and T are not equal. T2 prime and T are also not equal because there is a velocity involvement, right? This thing which I have appreciated long time back, okay, in 3 4 classes we have already talked about this. So this is T minus x2 v divided by c square. So this is just a mathematical idea of what we just discussed, 1 minus v square divided by c square. So we have this relation now. Okay, and if we just want to find out the difference, so in general here if you just consider this will be nothing but t minus t. What is the difference between the time when the door opens when you are inside this box? That is nothing but t minus t, which is 0. That means there is no difference in time, right? Similarly, if we just want to measure it in the moving frame when we are outside, so this would be something like t2 prime minus t1 prime. Now, if the event is simultaneous, even in the moving frame, they should give you 0, which it does not give, right? Because if you do the calculations, ये tt तो cancel हो गया, right? You can cancel out this tt when you subtract one from the other. You can take a minus sign outside and then just check it once. V divided by c square is there on top, okay? And then we have it as x2 minus x1, right? So x2 minus x1. So it will be x2 minus x1, right? यहाँ एक माइनस साइन है, इसकी वजह से यू आर गेटिंग अ माइनस हियर आल्सो. यू कैन डू द कैलकुलेशन. डिवाइडेड बाय root over 1 minus v square by c square. So what do we observe? We observe that this is actually not giving me a result which is equal to 0. So this is not equal to 0. So that means the time at which t1 opens and the time at x1 opens and the time at which x2 opens are different when we are observing it from outside when a frame of reference is moving. Okay, so if you look into this expression, t2 prime is equal to minus of something plus of t1. Okay, so you can estimate which one is greater, which one is lesser, depending on what is the scenario. So this is what is happening. Okay, so therefore we can simply say that t2 prime and t1 prime are not same, are not same. I hope you understand why we say it's not same, because t2 prime is equal to t1 prime minus v by c square, x2 minus x1 divided by root over 1 minus v square by c square. So in general, you can say, if you do the calculations here, t2 will be actually less than t1. Sorry, t2 prime will be less than t1 prime. Right? If you do the calculations, they are not equal. So they are not the same. Okay. Hence, they are not simultaneous. Hence, hence, they are not simultaneous. So this is your mathematical idea. So we developed our knowledge of relativity, considering the speed to be comparable to the speed of light in such a way. So now when we are actually discussing this actually seems to be clear, right? So I hope all of you that it's clear to you. If some of you, missed out, or maybe you just spaced out when I was taking the previous classes and all, okay, I'll definitely suggest you to go through all the previous lectures which are there available recorded, okay.